Well, thanks everybody for sticking around. Let's see, do I have a fake laser pointer here? Sort of. All right, thanks everybody. Again, I'm Jim Warner from NASA Langley. In the theme of trustworthiness for AI, we'll be talking about machine learning, specifically in the context of uncertainty quantification. So I think this talk will be a little more researchy, maybe, kind of in the modeling and simulation realm. I'm going to first talk about surrogate modeling as sort of the traditional use of machine learning for UQ. And then I want to get into some emerging research areas that are looking to combine machine learning with physics-based modeling to do uncertainty quantification. And we'll give a real quick high-level overview of 3 different methods and how we're trying to apply them to NASA problems. So zooming out at a high level, again, our motivations, modeling and simulation. So, we'll consider a general computational model. We'll have some input parameters going into the model, and we're going to be looking to make a prediction of some output or quantity of interest y, for example. So depending on our domain, this computational model can, have different meanings. In this talk, we'll consider a few different applications where this computational model will either represent trajectory simulation for an entry, descent, and landing application. Here, some of the input parameters that we're interested in are things like the atmospheric conditions and the mass properties of a reentry vehicle. We're trying to make predictions for trajectory state variables like the landing location in one instance. We'll also talk about a reliability analysis where we're considering a spacesuit impact model. So here, we're trying to model an astronaut potentially falling on the lunar surface. So some of our input parameters are the impact velocity, basically describing how fast they might be falling, and the properties of the lunar regolith. And we'd be trying to predict the max contact force to understand any resulting damage. And finally, we'll talk about materials characterization application, where we're considering a simulation of mechanical testing. So we could vary things like the applied load and material properties and try to predict the mechanical response there. The field of uncertainty quantification considers the fact that the model is not a direct reflection of reality. We also might not know the specific values for our input parameters that are going into the simulation. So instead, we would represent our inputs as, for example, probability distributions, as you see here. And depending on the application, we might be looking for different information coming out of our computational model. So in a simple case, we might be interested in just statistical estimators like the expected value. So what is the expected behavior of our system under uncertainties and some of the input parameters? We'll consider that in trajectory simulation later in the examples looking at predicting the expected landing location for a reentry vehicle. We also might want to put together confidence or credible intervals for our quantity of interest, so identifying something like the 95% confidence interval or the confidence landing ellipse when we're considering trajectory simulation in a landing location. Of interest a lot, oftentimes at NASA and engineering applications, is essentially the probability that something goes wrong. So the ability to estimate rare events and percentiles and understanding the tails of your distribution. We'll consider reliability analysis of a spacesuit later, where we're trying to predict the probability of failure or the probability of exceeding some critical value of our output. Whoops. All right, so those are all instances of what we call forward problems. So we're assuming we know uncertainties in the inputs. We're trying to predict something about the output. We can also talk about the inverse problem, where we instead take measurements of our output. So we have some measurement data, and we're trying to use that measurement data to infer something about our input parameters if we don't know them. So actually try to predict what the probability density functions of our input parameters are, given that measurement data. I'll give an example of this later in the talk, where we're trying to characterize material properties given some mechanical testing data. So the main theme here for uncertainty quantification, regardless of the type of problem you're solving, forward versus inverse problem, or the statistics you're getting out, is the need to repeatedly evaluate a computational model. And this is also the challenge with UQ is the computational complexity then. So typically for a UQ analysis, you might have to run your model anywhere on the orders of thousands or even millions of evaluations. With these high-fidelity physics-based simulations like we have here on the slide, these take on the orders of minutes or hours or even days to run just one. So obviously this is a computational challenge, and it can be intractable to do so with high-fidelity physics-based models. So the focus of today's talk is really on how do we do modeling for UQ. So how are we actually making predictions within a UQ analysis? In general, there's these two classes of approaches. These are the physics-based models that we talked about on the previous slide, or data-driven modeling using machine learning. Each have their own inherent strengths and weaknesses. So we usually rely on physics-based models because they are interpretable. They have interpretable predictions. So as a domain expert, you kind of have an intuition on how predictions are going to change as you adjust your input parameters. They're theoretically rigorous in the sense that, usually we have a lot of, mathematical proofs of convergence and uniqueness of solutions with methods like the finite element method and finite difference method. And also, we usually have historically proven legacy codes, or we often do. So we'll talk about an EDL code from NASA Post 2 that we've been using for decades, build trust in that type of model. Downside, as I alluded to, so computationally intensive. It can be impractical to plug these models into a UQ framework, and also slow to develop and deploy. So building one of these types of models from scratch can take a really long time for anybody who has tried to do this in a small team or by themselves. All right, so it's usually the computational intensity that drives us to try to adopt machine learning for UQ. So, in this context of using machine learning for uncertainty quantification, we're usually assuming that the data that we have is coming from the original physics simulation. So in that case, we refer to the machine learning model as a surrogate model or response surface or metamodel, essentially a replacement for that original physics-based simulation. So strengths and weaknesses here. Again, usually when you're using machine learning model for UQ, you're doing so to get efficiency. It's also typically faster to deploy these types of models, which we'll talk about as a double-edged sword. So I think somebody mentioned it's become too easy to develop models now, and that can lead you into some problems if you're not careful. So it's fast to deploy because there's so many libraries out there to implement machine learning now. So the downside, though, they lack the interpretability that physics-based models have. That's brought about the term the black box, so we don't often know why we're getting predictions that we are using a machine learning model like deep learning. And then finally, ineffective for extrapolation or sparse data sets. So your machine learning model is only going to be effective and trusted where you actually have training data. So trying to extrapolate beyond that is essentially dangerous. All right, so if you look at these lists of pros and cons here, strengths and weaknesses, a lot of them complement each other. You'll notice that, and that's given rise to a lot of different research areas that are now trying to unify physics-based modeling with machine learning and data-driven approaches. So today, in kind of the meat of the talk, we'll talk about some of those research methods, give a quick high-level overview. But first, I'm going to kind of give an intro to surrogate modeling, kind of the standard use of a machine learning model within a UQ framework. Then we'll get into some of these research topics, give a really quick overview of 3 different methods that you see here and how we're trying to apply them to problems at NASA, and then I'll give a summary. Okay, so quick intro to surrogate modeling. Again, the context here is we have a high-fidelity model, a physics-based model. We want to do UQ, but it's too expensive just to plug this model in directly. So we want to replace it with a machine learning model. So the first step is to run this model, many times up front. So you need to generate training data. So you select a grid of points or randomly selected points as inputs. You run each one of those through the model and store the outputs. At this point, it's essentially a traditional standard, supervised machine learning problem. Use any variety of regression, interpolation algorithms to learn this map directly, essentially from, your inputs directly to your outputs. And deploy that model as a surrogate then for UQ. So you can do something like a Monte Carlo simulation now much more efficiently with that surrogate model. We typically refer to all of this work that's done up front. The running of the high fidelity model, the training of the machine learning model is the offline phase. So it's sort of a one-time upfront cost that you put in. And then once you deploy that surrogate, you can kind of use it for online analyses, and do rapid analyses. Pretty much as you want for different scenarios. And this is just a snippet of code. So this is scikit-learn from Python, but again, there's tons of different libraries out there for different languages. This is just an illustration of how easy it's become to train a machine learning model. So ALG just represents any number of algorithms in scikit-learn that you can kind of plug in and test accuracy of. So as I mentioned, it's become so easy with just a few lines of code, you can build a surrogate model. And again, that can, lead you into trouble if you don't exactly know what you're doing. So kind of the key, I think, to surrogate modeling, and it's really just kind of like machine learning 101, is to always validate your model before deploying it. So, the key there is to always create a separate data set to use for testing that you don't let the algorithm see for training. And this guards against the common problem of overfitting in machine learning. So basically, overfitting is when your model works really well or has really low error on your training data, but doesn't generalize well. So, what that looks like is essentially, splitting up your simulation data and pulling off a small amount for testing, usually 10 or 20%, depending on how much data you have, and doing different comparisons of your surrogate model with respect to the high-fidelity model. So, this can be visualizations like the scatter plot to kind of, visualize how accurate your model is in different areas of your prediction space, calculate different error metrics, and kind of gauge whether or not that surrogate's sufficiently accurate for your application. So, oftentimes a third data set called the validation data set's used during training to tune any hyperparameters for your machine learning algorithm. So this can be things like the architecture for your neural network, choosing the number of layers or nodes in the network. You can, select the best values for these parameters using that validation data set. It's important to note that a lot of machine learning packages will sort of do this for you if you know what methods to look for. A lot of packages will implement cross-validation to select these types of parameters. Finally, if you've assessed the accuracy, your errors are non-negligible or maybe a little bit high for your application, depending on what your problem and application is. You can factor these errors into your total uncertainty when you go to do your UQ analysis. So, a simple way to do this would be to look at the empirical distribution of your errors, and you could sample that distribution when you go to make predictions within a UQ framework to take that into account. All right, summarizing some pitfalls and challenges. These are the two that we just talked about. So not validating the effectiveness, or probably even worse is validating using your training data, which gives you a false sense of accomplishment or confidence in your model. Not accounting for any errors when they're non-negligible. So in general, if you use a surrogate model for an estimator, it's going to be biased just due to the error with respect to your original high-fidelity model. Trying to extrapolate outside the range of your training data. So again, you can't trust the surrogate model where you don't have training data, especially for extrapolation. And then finally, when you have a sparse training data set, so if your high-fidelity model is really expensive, you can't generate a lot of data, you can get a pretty ineffective surrogate model, especially when you have a lot of input parameters for that surrogate. All right, so again, the main idea with the surrogate model is the replacement of a high-fidelity physics-based model, so substituting in a machine learning model. We want to now talk about some emerging research areas that don't get rid of the physics-based model, but try to use both in conjunction, or to keep the physics knowledge around at least when you're doing machine learning. So these are kind of three diagrams or motifs for three different methods that kind of leverage this concept. First, we're going to talk about multi-model or multi-fidelity Monte Carlo. This idea that we want to fuse predictions from a machine learning model with a physics-based model, so two standalone models, into one unified prediction for estimators and statistical estimators for some quantity of interest. We'll talk about physics-informed deep learning, so an idea that we want to train a machine learning model by integrating physical laws into the training process in addition to any training data that we have. And finally, we'll talk about active learning, which was talked about a little bit earlier as adaptive sampling or sequential design. This idea that we can guide where we want to collect training data with our physics-based model using the machine learning model. So a way to collect training data where it matters the most when your model is expensive. And we'll talk about these three methods in the context of some applications at NASA. All right, first one, so multi-model or multi-fidelity Monte Carlo. We're actively working on applying this to a problem in entry, descent, and landing right now. So a model that is a trajectory simulation. Our ultimate motivation in this project in particular is to develop high-precision guidance software for EDL, so ultimately trying to do trajectory optimization. So the technical challenge we're overcoming right now is the need to do uncertainty propagation and to do it fast and accurately. As we talked about, if you just try to use a high-fidelity simulation to do Monte Carlo, it can be too slow, right? So using your accurate model can be too slow. Using a surrogate model is fast, but it can be inaccurate or create biased estimators. So the promise of multi-fidelity or multi-model methods is that you can kind of get the best of both worlds. You can get the accuracy or the unbiasedness of the high-fidelity model with the speed up from the low-fidelity models. So we are applying this concept right now for EDL. Here's a kind of a diagram of what we're trying to do. We have, probably dozens of random variables going into the simulation. We're developing different low-fidelity models and trying to use those in conjunction with a high-fidelity trajectory simulation model to make fast predictions of statistics. So quick one-slide look at just some recent results that we got in this area. So this is predicting the landing location for an umbrella heat shield that's re-entering the Earth's atmosphere. In this case, we had a high-fidelity model that is a legacy code from Langley called POST2. That's our high-fidelity, our accurate, expensive simulation. Then we had a low-fidelity model that was a support vector machine surrogate model, essentially. So here's a summary of some of the results. This is the error in predicting the expected landing location versus the amount of runtime. So this is mean squared error, essentially how our accuracy increases as we devote more computational resources to the estimator. In the red, we have doing Monte Carlo simulation with only the high-fidelity model. Blue is using only the low-fidelity model, then black is combining them in a multi-fidelity prediction. And the takeaway, as you see in the plot, is that high-fidelity Monte Carlo, as you expect, it takes more runtime to get the same amount of accuracy as the other methods. The low-fidelity Monte Carlo has this, interesting behavior that you have an irreducible error once you get to some point. And that's because the surrogate model itself has error associated with it. It's not a true reflection of the high-fidelity model. So you reduce the error really fast, but then you plateau and you can't reduce the error any further as you increase the amount of resources. And then the multi-model approach is, both more efficient than high fidelity, and it's also unbiased. You see we continue to converge with that black line. And this log-log scale, in a lot of cases, we're getting about an order of magnitude improvement in computational efficiency. So moving on to the second method, we're going to give an example of how we're trying to apply physics-informed deep learning now for the problem of materials characterization for additive manufacturing. So again, the motivation here is additive manufacturing, where it's well known that we get a lot of variability in the material properties for specimens produced by additive manufacturing. So here we are trying to run some mechanical tests in the lab to get a sense and estimate the variability that we're seeing in our material properties using this type of method. The challenge here is we need to solve a really high-dimensional probabilistic inverse problem. So we're trying to estimate the stiffness in a specimen, which varies in space across the specimen, but also varies from specimen to specimen. So we're trying to capture both spatial and inherent variability of the material properties. The method we're using is called a physics-informed generative adversarial network, or PyGAN. So sort of a mouthful, and I'm not going to give all the technical details today. But the main kind of idea here is that a GAN is a state-of-the-art generative deep neural network. The cool thing about a GAN is that it's able to learn probability distributions based on some sample data from it. So we're trying to leverage that idea to measure some deformation from test specimens in a lab and train a GAN to learn the distribution of those properties from some test data. The physics-informed part allows us to relate material properties to the thing that we can measure. So it allows us to solve the inverse problem. And by knowing physics knowledge in this problem, we can use theoretically smaller data sets to get these estimates. So this diagram on the bottom kind of shows a bird's eye view of what we're trying to do in the project. So we're using digital image correlation, which is a technique that gives you full field deformation data about some test specimen under load. trying to run just a small amount of tests, train a PyGAN from that data, and be able to essentially produce results from an unlimited amount of tests that are, agree with that test data that we got, but is also physically admissible based on the physics. So far, this method, we've only tested in sort of like a proof of concept mode. So this is a synthetic data example, simplified 2D example, where here we've trained a PyGAN to generate samples of a log normally distributed and spatially varying material stiffness, using only deformation data, so it's solving an inverse problem. So here's a picture of the domain. We're essentially simulating a test where we're pulling on a plate in tension, and we're assuming that these plates have stiffness variability from specimen to specimen that we're trying to estimate using a PyGAN. So that's a look at the deformation data. Here we're giving it a lot of data, so it's not very realistic right now. Again, a proof of concept, so we're assuming we have 1,000 tests here where we've measured the deformation data that was actually simulated. So we solved the inverse problem using the PyGAN. So this is a look at samples produced by the deep learning method, the PyGAN, versus reference, so what we assumed to be the true material distribution. These are not going to agree exactly because it's sample randomness here, but we see qualitatively we're getting similar looking stiffness results from the PyGAN as we are from the reference distribution. To more quantitatively assess the performance, we looked at the statistics as well that the PyGAN is able to recover. So this is looking at the estimated spatial correlation. So we see in the dashed lines we're recovering the spatial correlation pretty well using this method, solving the inverse problem. And we're also estimating the point-wise probability distribution relatively well too. So again, proof of concept because this is synthetic data and it's a lot of data, and that's kind of the challenge now is how little measurement data can we use and still get accurate estimates of what the material properties are. All right, so one final example to finish off, we'll talk about active learning for reliability analysis. So here, our motivation is doing reliability analysis for the new XEMU spacesuit. The technical challenge with doing that is we're trying to predict a really small probability of failure. And the model that we have at our discretion is really, really expensive. It takes about a day to evaluate. That using a standard surrogate model for a problem like this, when you don't have a lot of training data, you're probably going to have pretty inaccurate predictions of the extreme behavior of your computational model. So it's really hard to predict what's going on in the tails of your distributions when you don't have a lot of training data with the surrogate. The approach that we're using, we're actually working with Virginia Tech right now, Bobby Gramercy and a couple of his students, to develop new active learning approaches that develop Gaussian process surrogate models that are tailored to make accurate failure predictions. So we've come up with an adaptive sampling technique that puts more samples near the failure region in your input parameter space. And that's sort of shown. This is pretty much the only technical details of this work is shown here. We have 4 random variables going into a high-fidelity impact model, and we're using active learning here to essentially identify where we have failure in terms of our input space. And we learn to put more training data near that region so that we get more accurate predictions with our surrogate model there. So here's an example of how that performed on a case where we're trying to estimate the impact failure in a spacesuit. So I'm comparing 2 surrogate-based solutions here, sort of a standard Gaussian process or randomly sampled training data versus a Gaussian process trained using active learning in this way. So here's a look at where training data is being selected compared to where the failure threshold is. So the main takeaway of this plot is that the active learning approach in blue is learning to put more training data along where that failure threshold is. So, more training data near failure means we're have higher accuracy for predicting pass versus fail. And pushing that through to actually estimating the probability of failure. So here, we don't know the true answer for probability of failure, but all we can say is sort of circumstantial evidence. We have a smaller confidence interval using this active learning approach, overlapping with kind of the high-fidelity Monte Carlo estimator, but using just a fifth of the model evaluations here. So again, super high-level look at this. We have a paper out on this idea with a lot more technical details that you can look up if you're interested. All right, so to conclude, Talked about machine learning models for UQ. So first talked about surrogate modeling, which is used a lot for UQ, and how to kind of do so responsibly. I think the main thing, just like machine learning 101, always validate your machine learning model or your surrogate model prior to deployment. Always use a separate testing data set that wasn't seen during training. Avoid extrapolation outside your training data range, and then account for any non-negligible surrogate errors in your analysis. Talked about some emerging research areas that I think are pretty interesting, that combine physics-based and data-driven approaches. Idea of multi-model Monte Carlo, physics-informed machine learning, and then active learning. So again, super high level. Have some references here if anybody's interested in more of the technical details there, and also happy to take any questions now. So thanks for sticking around through the break and watching.
Come on down. Are there any questions on Skype or Zoom or whatever?
It's a long walk.
It is a long walk. Mikhail Smirnov from here at IDA. So this is really cool. I was a little bit surprised. I suppose that physics is not my area at all, but I thought that if we had a physical equation, if we had a model that truly represents the world, and it was just expensive to evaluate, we would spend a lot of effort making it faster to evaluate, or looking for actual simplifications, approximations we could explicitly make, because that would give us, I know we talked about transparency not being the end all here, but it would give us some transparency and we could understand what our simplifications do versus a black box machine learning approach. So how do you, like, you've got this model, it's expensive, you could either work to simplify it and make it faster, or you could do this hybrid approach. How do you decide where to spend your time and effort?
That's a really good question. So I think the main emphasis with a lot of these methods, like especially multi-fidelity Monte Carlo, is we spend all of this testing and validation effort for this high-fidelity physics-based model, that we want to do whatever we can to keep that model in the loop or involved somehow, right? So I think it depends on what you're after. So this multi-fidelity Monte Carlo method I think is great, but it's limited to statistical estimators like expected value. So if that's what you're after, I think that method works great, and sometimes you only need to run your really expensive model a handful of times, 3 or 4 times, and you can reduce the variance of your estimator using these faster models. So I think I would use that if that's all I was after, statistical estimators like moments and things like that. When you're looking at reliability and you're trying to predict a probability of failure that's 1 in a million or something, and you need tens of millions of evaluations, like even a simplified physics model is going to probably be impractical for something like that. So yeah, I think it depends on what you're after, but I'm not a machine learning kind of maximalist. I think if you can use the physics-based model, you should. We spend a lot of time developing those and have more trust in those, but I think it's application specific in the end. Thanks for the question. Yeah.
Hello, Logan Osman. I'm with IDA also. Actually, my question is sort of related to that one, but I think it gets to how careful do you have to be about choosing the physics model? Because some of the physics models themselves are effectively black box models, parameterized based on experimental data, not necessarily first principles, or even some of them are first principles, but with lots of assumptions. And so are you throwing uncertainty on top of uncertainty here?
Another really good question. So you're talking like a lot of these physics-based models have phenomenological models that are just fitting a bunch of constants to some test data. I think that speaks to kind of the broader need for uncertainty quantification at all the levels. So one of the big sources of uncertainty is just the model discrepancy, like that's not inherent in just the parameter uncertainty. So understanding the discrepancy between your model for a best case scenario versus test data but then also incorporating parameter uncertainty. So you do that through something like a model calibration. Can you understand uncertainty, even if it's, these constants that are calibrated to data? Can you at least do that with uncertainty, so you have a, understanding of the range of those constants? So I think, yeah, you need a more comprehensive UQ approach, regardless of the type of model that you're using. And folding in a machine learning model only layers on that uncertainty that needs to be taken into account. So, yeah, I don't know if that truly answers the question, but yeah, I don't know. Do you have a follow-up on?
I think the only thing I could say is that for some of the, you mentioned some of the pros and cons for high-fi physics versus machine learning. I think some of those pros and cons on the machine learning side you also actually find on some of the physics models, and that they're simplified to be faster than the more exact result, and you lose interpretability.
Yeah. No, that's a good point. So, yeah, black box is often associated with physics models, too. You're right there. So, yeah. Thanks.
One more, sure.
Hi, Dan Lugar, IDA. Thanks for the interesting talk. My question is about, you mentioned and you gave an example of using the surrogate models to do solving the inverse problem, finding the effects from the cause. Finding the cause from the effects. My question is that this is a notoriously ill-posed or ill-conditioned problem. And so when you're trying to calibrate the cause, you can sometimes have wide uncertainties, even with a mechanistic physics-based model. Are you finding that with the surrogate models that you're getting accurate uncertainty bounds when you do the inverse problem?
Another very good question. So me and my group are spending a lot of time reading about calibrating model discrepancy in addition to parameter uncertainty right now, which only blows up this problem of uniqueness and well-posedness of the inverse problem. So I think, yeah, this is a big challenge for UQ is calibrating and doing so with appropriate uncertainty. I think one approach we're looking at it a lot now is kind of optimal experimental design or design of experiments. How can we design the experiment to reduce uncertainty in our calibration? So that's one thing we're definitely looking at, is how do we have a goal-oriented design of experiment to help with the calibration kind of downstream. So I think that would be the best thing I could say, is that it really depends on having the right data to get a good calibration. And sometimes you need to have measurements of multiple quantities to really pinpoint what the parameters of the model are. So sometimes, just one measurement of one response is not enough to really drill down on what the causes are that you referred to. So, yeah, I think that's kind of an open question in this area. So, thanks.